I would like to welcome everyone to our webinar today, an introduction to arc flash analysis in EasyPower and EasySolv. Some of the topics we'll be looking at include faulting buses and arc flash results on the one line, incident energy at working distances, arc flash boundary, arc flash hazard options. Some of the options that we'll be looking at include the calculation standard used, using worst case arcing currents, the output values with including, excluding, both in detail, and we'll go into more detail about those. And then looking at max times. We'll also look at the arc flash hazard report, the arc flash labels, energized work permits, scenario comparison report, and arc flash using the coordination focus. And then at the end we'll follow that up with any questions that may come up. So let's continue to EasyPower. So here's the screen. It shows the EasyPower software. Today we'll be looking at both EasyPower and EasySolv. I will be using EasyPower exclusively, but I'll show you the differences when they do come up as far as the differences between EasyPower and EasySolv. So when you first open EasyPower and you have your one-line model complete, you'll be in the database edit focus. To access arc flash, you'll need to go under the short circuit focus. So if I click on short circuit, you'll notice that the ribbon changes. And let's quickly go over some of the buttons in the ribbon. We have the fault bus button, and this will fault the buses on the one line. We also have a work permit button that refers to arc flash. Now on the one line display, because this is short circuit focus, there are many short circuit options that are available. The one we'll be focusing today on is arc flash, and you'll notice up here in the ribbon is the guy that is kind of on fire with a fault. That will be the button that needs to be pressed in order to show arc flash results on the one line. We also, for most faults, will be needing the three-phase fault, and that button will be need to be pressed as well. There's also some buttons for some short circuit options, or we'll be going for arc flash options, and then some short circuit result reports, which we won't be dealing with today. We'll talk about the scenario manager and how to perform the scenario comparison report. And then there's some other tools as far as inserting some notes, clearing the results, finding copy. There's also some others that are in the database edit focus, including zoom and changing between windows. We'll also use the arrange for arc flash button, and you'll see how this works in a little bit. So that's a quick look at the different buttons that are available in the ribbon. So let's begin by pressing the fault all. And if you want to fault all, you just press the button. And since we have the arc flash button already pressed with a three-phase fault, you'll notice that the results show on the one line. So the actual arc flash calculations that are performed by the software go rather quickly and show quite a bit of information. So let's go down to switchgear 4. So for the arcing fault that we've performed, the arc flash boundary is 98.5 inches and the incident energy is 14.7 calories per centimeter squared at 18 inches. If we go over to, say, panel 2, it has an arc flash boundary of 237.5 inches with an incident energy of 82.7 calories per centimeter squared at 18 inches. So it's important to note that when we talk about the incident energy, it is associated with a distance, because the distance the distance you are from the arc will have an effect on what the incident energy calculation is. The arc flash boundary is the point, or is the distance from your equipment that you're working on where the incident energy is at 1.2 calories per centimeter squared. And basically that's the point where your worker or the worker needs to have the appropriate PPE on, or needs to be wearing that for their personal protection. If you only want to fault one bus, you can just double click on the bus, or if we want to just do a group select, you can just select those items and fault, and only those items get faulted. The one-line results currently show it shows the arc flash boundary and the working, or the incident energy at a working distance. Now there's a lot more information that goes into obtaining those results. And if you click on the Arrange for Arc Flash button, it'll pull up a arc flash hazard report. It comes up at the bottom of the screen, but I'm going to maximize it, click the maximize button so we can get a better view of it. And you'll notice there's quite a bit more information that's shown. And we have the bus name. So earlier we were looking at switchgear 4. So it tells us what the arc fault bus KV is. We know what the tripping device name is. So if we minimize this again, let's look at this. So it shows BL1, breaker BL1 is our tripping device. So this is a fault on the switchgear where the breaker BL1 is the tripping device. So it's, in this case, it's not for work on BL1, it's for work downstream of BL1 where it can be ensured that the main breaker will be the tripping device. The upstream trip device function column is really for relays. It'll tell you what function is being used. The equipment type is the type of equipment, and that is specified in the bus dialog. We'll go through that a little bit later, but we've specified it as switchgear. The switchgear sets the arc gap, which in this case is 32. You'll notice down here on MCC1 that the arc gap is 25. Then we get into some of the currents. We have the bus voltage fault and the bus arcing current, and these are the currents that are used to calculate the actual incident energy. There's also a branch arcing fault current that can be shown in the report, and that is used to determine what the trip time is. So every device has a TCC curve, and basically what happens is at the fault current, it's the branch fault current, or for a fault that goes through here, the current that's shown through this branch is used to determine what the trip time is. So he uses the fault current with this in the TCC, determines how long it takes to trip based on the manufacturer curve, and then we have the arcing time, which is 34 seconds. The trip time is the actual trip time on the TCC curve. The opening time would be any extra time. For instance, if you had a relay with a breaker, this would be the breaker opening time. In this case, since this is just a breaker, it is there is no opening time because it's included in the trip time on the TCC curve. We show the arc flash boundary, which is 98.5 inches, and then the working distance and the instant energy. So these three results here are what are shown on the one line. But there are many other factors that go into determining what that information is calculated to be, and that is shown here. In the arc flash config button with the arc flash hazard report selected, there are many different functions that you can show in this report, and those have been discussed in another training video. If you go to the EasyPower.com website and click on the left, you'll see a button for training videos. If you scroll through the videos, there's a video on arc flash hazard reports, and it'll go through and discuss a lot of these different topics in more detail. I'm going to show one that has the branch currents, and you can make your own configurations. And so now I've added the two branch currents to this. So you'll notice here that the current through this breaker is 18.706 kA with an arcing fault current of 10.168. So this 10.168 is used to determine this trip time. So I'm going to go click on the short circuit options button on the top left, or in the ribbon. There's an arc flash hazard tab on the left that needs to be selected. And if you pull that up, you'll notice here the different options that are available for arc flash. First, I want to draw your attention to the arc flash spreadsheet. If this is not checked, then you will not see the report that we've just been looking at right here. So if you don't see that, that's the button that needs to be pressed. We'll take a quick look at some of the options here at the top of the window. There are 4 different standards that EasyPower supports as far as the calculations. The IEEE 1584 are the ones by default that we use or recommend being used. The NFPA 70E 2009 D.5, D.6 plus are other equations that are used. We feel that with the IEEE 1584, these are from the 2002 release of the 1584, and it seems like they are used more widely in industry, and there's more test data that they were developed from. The V6.0 Enhanced and V7.0 Enhanced are proprietary equations that are based on the IEEE 1584. If you get to certain voltages, you may see, or if you get to certain voltages in the IEEE 1584 equations, you may see, for instance, an arcing fault current that is higher than the voltage fault current, which is not a realistic result. So these equations here are attempts to improve upon those discontinuities. But if you use the IEEE 1584, that should be sufficient as a standard. And that's what we'll use throughout this this webinar. The worst case arc flash hazard. There's 4 different options that are available. And to begin with, we've started on including main. Including main, as you saw here in this first example, is where the main is used as the tripping device. So if in order to do that, you'll want to make sure that your main device is isolated and barrier protected to ensure that if there is an arcing fault downstream of that main, that device does not become engulfed within the arc. If that is the case, and you can't ensure that your arc or that your main is going to trip as advertised by the manufacturer, then using the excluding main would be the ideal option. And if you don't know or you're new to this, I would recommend just leaving on excluding main, and then as you see issues arise as far as incident energies, then go back and look at it. But if you use excluding main, that's your most conservative result. So I changed that to excluding main, and I'm going to click on the open button. And you'll notice here now that our fault current or our incident energy at switchgear 4, and I'm just going to double click so we only have one report or one row in the report. You'll notice that the incident energy is now 99.7 calories per centimeter squared at 18 inches and with an arc flash boundary of 361.7 inches. Switchgear 4 here, you'll notice now the upstream trip device is R6. So if we go further upstream, this is our relay R6 is our tripping device. That's because we've now excluded this breaker BL1. It's no longer the tripping device. So you'll notice that it shows the trip function that's used, and then the following stuff is still similar. So it's switchgear. It's grounded. The ground, whether it's grounded or not, has a small effect on the result with a gap of 32. So the voltage fault current at the bus is used for the calculation of the incident energy, and you'll notice now that our branch current is much smaller than it previously was when it was going through breaker BL1, and that's a result of the current on the primary of the transformer as it goes through relay R1. It's now at a different voltage, and so it's been calculated based on the current at that different voltage. So you'll notice in 0.3 second, or about 3010 amps, that for arcing fault current it takes 2.67 seconds for the relay to trip. Now we have a breaker opening time, as the relay is associated with breaker BH3. It's a 5-cycle breaker, and adding that together gives us an arcing time of 2.753 seconds. And that's the information that it takes to show that 99.7 calories at a working distance of 18 inches is the result. The third option is both, and that includes both options we've just been discussing. So it'll show both options. So we have a BL1 and an R6. So this is the including option, and this is the excluding option. The fourth option is a detailed option, and this is the one that's the most difficult to understand, and I'll bring this up so that we see all of the different options, and we'll bring this up a little bit. So the first two columns include the including and excluding results. Now you'll notice there's three other results, and there's a result for each of the feeder devices: BL2, BL3, BL4. So let's just take a look at BL2. So what we're looking at here is this is the incident energy, which is 8.2 calories per centimeter squared at 18 inches. This is right on the load side of breaker BL2 if the work is being done outside of that device, where it can be ensured that it will not become part of the arcing fault and be included, and trip as described by the manufacturer. It's not for a fault down here at MCC1, even though it's using that BL2. It's for a fault just on the load side of that breaker. So if we fault the bus down here, MCC1, you'll notice that it's 7.6 calories per centimeter squared. So if we do it just on the load side, it's 8.2 calories per centimeter squared. So there are applications for this, but again, if you're new to this and you're not sure, I would recommend staying away from this until you're completely sure. And the only time you would really use this would be on a switchgear equipment. So I'm going to change back to both including and excluding and say OK to that. So going back to the arc flash options, the next thing to talk about are the max times. Now, in the IEEE 1584, there's a comment that talks about if a user or a worker is in the area of an arc flash, if they can get away from that arc flash and be removed from that area within 2 seconds, then you could use a max time of 2 seconds. And there are times where that case may be good for your use because it can help reduce the incident energy and make it or reduce it to a level where energized work can be performed. Now, it is something that you need to look at on a case-by-case basis, but I will demonstrate how that works here. So if I just, under our voltage 0.25 to 1 kV, so 250 volts to 1000 volts, if I say OK to this, you'll remember that our R6 was at approximately 2.7 seconds, if I remember correctly. Now even though it continues, it drops at a time of 2 seconds. So that has reduced the incident energy to 86.3 calories. It has not affected the including result because it's still only 0.34. It's only if it goes above that max time. That's where you could specify that that result. There's another option here. And I'm going to change this back to 1000 for the rest of the webinar. Use worst case arcing current. There's a in the IEEE, due to the fact that the equations are based on probabilities and the actual arcing current is really unknown, we look at multiple. It's it's described to look at two cases for low voltage buses which are less than 1000 kVA. And so we look at 100% of the calculated arcing current, and we also look at 85% of the calculated arcing current. These are numbers that the user can adjust and change those to what you would like, but they are there. That's what they do. I'm going to say OK to this, and you'll notice here that we have some results in black and some results in this magenta pink color. The ones that are in the magenta are 85% results. The ones that are in the black are the 100% results. So that's how we differentiate. If you print this out, you'll see an asterisk included on the currents, and that'll give you a heads up that that's an 85% current. So there's a few more things just to briefly discuss on the options here. We have been using the momentary current as our current to determine the trip time and the voltage fault currents. You could also use the interrupting or the 30 cycle currents. But we use the momentary by default because they are higher and assumed to be more of a it'll give more of a conservative result. That may not be the case, and sometimes if you're looking at a condition where you're in a plant shutdown or something like that and most of your motors have been removed, you may want to look at how your results are under a 30 cycle result. There's also an integrated method, and that is a way that you can increase or the arc flash energy are accumulated over time, and as the currents change in your system as you go from a momentary to an interrupting or a 30 cycle current, those get adjusted, and also if you have multiple sources and one gets shut off, the system will update and accumulate that over time as the system changes. And this format, the integrated method, is probably best used if you're looking at multiple sources. That's where you'll see the biggest difference. If you're looking at a system that is a radial system that has very few motors, then the momentary and the integrated should give somewhat similar results. You can show your working distances in different options, and then the working distances are shown down in the table here. There's enclosed and open air distances that you can specify, and so there's two different tables. But you can choose the ones that you want, and if you go back to the report and push the plus button and expand it out, you'll see those different results. So as I said earlier, as you gain distance, your incident energy will be reduced. So on the case of switchgear 1 for work downstream of the main, if you go work at 36 inches, then you have reduced your incident energy from 14.7 to 5.3. There's also a threshold incident energy and a threshold report. This is just when you fault the bus, if the incident energy is above this calories, it shows as red. If it's below, it'll show as blue. It's pretty straightforward. If you want to make any changes to that, that's available. And then there's also an advanced option button, and I just want to show you one quick thing. In the 2000 or prior to the 2012 release of the NFPA 70E, incident energy calculations were associated with a PPE level. In the 2012, the NFPA 70E decided that they wanted to split up PPE levels, and from incident energy calculations. So in the software by default we don't show PPE levels, but if you do press this button and change to this and say OK, it will go back and show the incident energy and the PPE levels based on prior to 2009. If your facility is still on that method, that option still is there, but in light of trying to keep with the latest NFPA 70E, we have removed that from the default options. But it is there if that's something that you like to have. One other quick thing is, as you get into higher voltages, there in the NFPA 70E 2009 Annex D8, the high voltage open air buses can be adapted to this. So this is for open air buses, and it requires a single line to ground fault. So basically you'll need to, if you do have open air high voltage buses, you would click on line to ground fault, and you'll notice that for this, because it's enclosed, it says only 3-phase faults are supported with arc flash. So going back to that. So that's a quick review of some of the options and the arc flash hazard report. I'm going to say no to this and go back to the database edit and pull up a bus dialog. So in the arc flash report, we showed the different type and how it mattered. Under the bus type, this is where it gets selected. So it kept, in switchgear 4, we have selected switchgear. If it's another type of bus, you would just select the type of equipment that it is. And then under the arc flash hazard tab, for each bus there are different options. Where we were talking earlier about including, excluding, and both, you can use the global option, which goes back to the options that we were just looking at, or you can do it per bus and make changes. One thing you could do is, in your global options, leave everything as excluding main, and then if you wanted something else for a particular bus, you could go make that change on a per bus basis. There's also the way that we have been doing it is to calculate the incident energy. You can also exclude it from the report, so that if you do click excluded and you fault that bus, it will not show in the report. Or you can force a bus to a particular incident energy. So if I was to say 4, I could go to the fault, and you'll notice that now it's 4 calories per centimeter squared. Going back to the arc flash tab, if I get rid of this and go back to calculated, you'll also notice that we do have some trip times. So by default, we default to TCC times as they're auto-calculated, and this will use the TCC and come up with the trip time. You can also use a user-defined time. So for instance, this could be used if you are missing some trip device. You could put in a max time of 2 seconds, or maybe you have a differential and you could put in a time of maybe it's R7, and you have a function type that maybe is a differential, 87 function. You could say OK, and then if I was to fault this bus, going into short circuit focus, fault this bus, now you'll notice that our arc time is just set to 0.1 second, which results in a much lower instant energy. So if you do have a case where you want to just force a trip time, that is the way that you would do that. You can just show both, and then the user-defined and TCC times. The other option would be a predefined fixed times. This is a legacy item from the library, and is a quick way that just shows results for different times. So if we go back to TCC times, that'll give us the results we've been seeing in the past. Now, there's some options for working distances. You could do it based on the global options or on the user specified time. And the orientation, by default we say it's vertical. In recent years there's been some testing done that based on how the bus is in relation to the worker, it will affect the arc flash instant energy. There is nothing that's been brought out currently from the committees that specify what those results are specifically, but this may be something that you have experience with that you want to in place and specify. And it is available, but that's what that is for. And then the final thing is labeling, which we'll talk about here in just a minute. But you can specify per bus how many labels you want to print, and have a label comment that's specific to this to this equipment. Going back to the arc flash report, so I'm going to fault these buses so that we get a few more buses available. There's some options as far as opening in Excel and exporting this report itself, so that those are available. You can also print the report. This is also where you would print your arc flash labels from. And we'll just quickly go over this. So I've clicked to print labels, and as this comes up, you'll notice that we have a preview of the different devices. I'm going to click on the select devices to show you which ones that we've specified. And there's a number of different templates, your page layout. This label comments here is for all the labels. It's different than the one that I just showed you. But there's a lot of different label templates that you can choose from. And you can also customize the labels. But at this point, if this is the label you want, you just press print. If your company or your client wants specific labels, you can design your own label. And you'd go in and you can either start from scratch or take a template and then click Start to Edit. And now you have a template and that you can start working with. That you can have conditional statements, and some users like to change the color, or as the instant energy goes up, change from warning to danger. So there are things you can do within this option, and and to make the label look like what you would like. So let's get out of here, and we'll go back to our report. So that's a quick look at labels. One other thing I would like to show you is that sometimes you'll want to include your on the one line, the arc flash results on a one line or in a report. And so if we just click copy and open in Word with nothing selected, if I paste, I can paste in a picture of the results into a Word document or any document like that for report purposes. So just wanted you to know that that's available. We also have the capabilities of doing work permits. So if you can either select a bus and right click, or you can click on the bus and click on work permit. So I'm going to click on work permit, and so we've done the switchgear bus, and you can pick whatever you would like, and I'm going to open the hinge doors as that's my task. And I can say OK, and you'll notice that I have just created this work permit. It describes the open hinge covers, and this is the equipment, and then tells you what your incident energy is, what your PPE, and these can all be developed per site. This is just a Word template with some variables in it that pull in the information from EasyPower, and then gives you the opportunity to get the proper signatures, and this follows pretty much the NFPA 70E example. So saying no to that, couple more things to discuss. One is in this sample, let's see, we have a scenario. So one of the conditions that you may get is a utility gives you multiple fault currents. So it might be wise to run both cases and see what what's the most conservative incident energy is. So in this case, we have multiple scenarios, and if you go to the bottom where it says create scenario comparison report, and we'll do one for arc flash, and I'm going to say discard the changes, and we get this scenario comparison report. I'm going to say create report, and you'll notice that you get a report that's very similar to the arc flash report, but you have multiple lines for the same bus. So in this case, you have a scenario base case, which is the one that we've been working in for the majority of the webinar here, and then our scenario that's minimum short circuit. So if you look here, under the base case, we get 1.3 calories per centimeter squared at 26 inches, and for minimum short circuit, we get 1.1. So let's go down to switchgear 4. So you can see under the base case, it's 86.3, and for the minimum short circuit, it's 65.3. So by having the minimum short circuit, you can see a little bit of a difference as far as the incident energy. Under the refiner bus, you'll notice that under minimum short circuit, it's at 34.8, which is a manageable level of incident energy, where at 45.8, it's now in that, it's above 40 calories, it's extreme danger. You need to take a look at it before doing any energized work to justify that that work needs to be done and how to properly protect your personnel. So this shows all scenarios. We can also just show the worst scenario. So this tells you, okay, the base case in all cases has the worst scenario. So if you're looking at printing labels or something like that, you probably just use the base case. You can filter this out more. You can also print it, and you can also print labels from this field here. So as you get more cases, as far as like with an ATS or a emergency generator, multiple utilities, multiple sources, things like that, this is a good tool for determining what your worst case arc flash is. So if I close this and go back to the one line, the final thing I want to do today is show the how you can use coordination for your arc flash. And this, for users with EasySolv, this is not available. Also, if you have arc flash and you have not purchased the Power Protector module, this is not available for you as well. But for those of you with Power Protector module, this is a way that you can use that to help with your arc flash. So I'm going to make one change. I want to show the including main result here, and I'm going to go into coordination focus. So we were looking at this option, and I'm just going to create a TCC and plot the TCC. So I've selected the equipment I want included in the TCC, and I'm going to plot it. So if I perform a arc flash on our switchgear 4, we have an incident energy of 14.77 calories per centimeter squared at 18 inches. Now, I can look at this. I can go back to the report and determine what the trip time is, but I know that we've chosen the including option for the arc flash result, so BL1 is my tripping device. If I right-click on that and click on Insert Arcing Current Tick Mark, this is the current that is seen by this device. So you remember earlier it took 0.34 seconds for that device to trip, and I'll try to make this a little bigger, but this is 0.3, this is 0.4. So right here, you can also, down here you'll see the XY coordinate. So if I hold Control, it gives me a cross arrow, and at the bottom you can see that at about that current, it's right at about 3.4. So it makes sense. So so this is how you can use the coordination focus to obtain the results you're looking for. Now, if you're actually doing a coordination study, the nice thing about this is you can drag the curve. So I've just reduced the short time on the curve, on the breaker curve, to the minimum setting, which now results in a maximum time of approximately 0.19 seconds. So you'll notice that our incident energy is now reduced to 8.2. You know that, but you have to do this as part of your coordination study. You just can't be making these assumptions. But this could be your option. So if it goes to max, it's 21. The other things you can look at are, prior to this, if your maybe your short time pickup is high, you could drag this and see, okay, at what point, how far down do I have to go in order to for it to hit on the short time setting. And so this is really advantageous if you're looking at that, or you're trying to verify your trip times in your report. But just wanted to quickly show you some of those options that are available. So closing the TCC, and we go back to database edit focus, and we'll say no to the changes. So so that's a overview and an introduction to ArcFlash within EasyPower and EasySolv. I hope that you've enjoyed the webinar and that it's been very informative and that you've learned quite a bit today. So thank you for watching the video, and we look forward to having you at one of our next webinars. Thanks.